Welcome to the International Symposium on Probability and Statistics, New Frontiers, organized jointly by the Department of Statistics, University of Calcutta, and Calcutta Statistical Association to celebrate 75 years of Calcutta Statistical Association. CSA was established in 1945 by a group of statisticians who were faculty members of the Department of Statistics, University of Calcutta. Right from the onset, the objective has been to promote activities related to statistics, and using the limited resources, the association still continues to play a key role in developing statistics. The association has always focused on advancement and dissemination of knowledge of statistics. The Calcutta Statistical Association Bulletin at all times paid due attention to quality of articles. Since 2016, it is being published by Sage Publications. The association regularly organizes lectures by eminent scholars from India and abroad. Since 1991, Calcutta Statistical Association, jointly with the Department of Statistics, University of Calcutta, is organizing an international symposium on probability and statistics every 3 years. The association completed its 75 years of glorious existence in 2020. As a part of the 75-year celebration of CSA, we organized a lecture series for propagation of statistics, education, and research. Of course, we were waiting for this worldwide pandemic situation to improve, but finally we decided to organize this online symposium to celebrate 75 years of CSA. As always, we have with us the Department of Statistics, University of Calcutta, as the co-organizer. May I now introduce you to the dignitaries present today. I feel honored to welcome Professor S.P. Mukherjee, former Centenary Professor of Statistics, University of Calcutta, and former President of Calcutta Statistical Association, as the inaugurator of this online symposium and the chair of the keynote address. It is an honor to welcome the keynote speaker, Professor Tathagata Bandyopadhyay from Dhirubhai Ambani Institute of Information and Communication Technology, Gandhinagar. Finally, I welcome all the participants to the International Symposium on Probability and Statistics, New Frontiers. Unfortunately, due to some unavoidable circumstances, let me see. Professor Monisha Pal, Senior Professor, Department of Statistics, St. Xavier's University, retired Professor, Department of Statistics, University of Calcutta, President of Calcutta Statistical Association, and Chairperson of this event, could not attend the inaugural session. However, she has sent her message for us, and I'll request our technical team to kindly share the message.
Respected Professor S.P. Mukherjee and other dignitaries present, and my dear participants, it gives me immense pleasure to be with you at the opening session of the International Symposium on Probability and Statistics. As you are aware, the symposium has been organized jointly by the Calcutta Statistical Association and the Department of Statistics of Calcutta University. The association has completed 75 years of its glorious existence, and this symposium is a part of the celebration of the same. The Department of Statistics, along with the association, has organized many successful symposia over the years, and I believe this symposium will also be a success. The symposium will have 6 technical sessions. The topics of these sessions bear great relevance to the present-day research and applications. I believe the deliberations in each session will be highly beneficial to all the participants, especially the young researchers. So, ladies and gentlemen, The takeaway from this symposium is expected to be high, and I request the participants to be present in all the sessions. Thank you.
Thank you, Madam, for the message. I'll now request Professor S.P. Mukherjee to inaugurate the International Symposium on Probability and Statistics, New Frontiers, and say a few words.
It is with a feeling of pride and pleasure that I join all of you on this memorable occasion. Friends, speaking on frontiers in any subject like probability and statistics, two things come to my mind. In one exercise or one type of exercise, I would say, the existing frontiers are pushed forward or they are expanded, and in the other, new frontiers are opened up. To me, it's quite difficult to distinguish between these two components of the frontier. I mean, expanding frontiers which are already existing and new frontiers which are being opened up. And talking about new frontiers, I may be excused if I make a mention about both these two parts of the exercise about what may be called new frontiers, because they are hardly distinguishable one from the other. Looking at this exercise to push the frontiers of probability and statistics further, I can also visualize several levels of efforts being put up by research workers in the relevant fields. Firstly, there are attempts to generalize, sometimes even modify and extend certain, so to say, concepts, methods, techniques, and corresponding results and theorems, which were taken up earlier in a somewhat restricted context to a wider framework. For example, certain attempts to get from the univariate data setup to the multivariate data setup, from univariate surveys being designed to multivariate surveys being talked of, from estimation of parameters in a restricted space to those who are in the unrestricted space, or going from estimation of factorial effects where the factor space is unlimited or unrestricted to a situation where the factor space is itself restricted. These are important developments, no doubt, and can be clubbed together in terms of frontiers of statistics, of course, based on probability. A second dimension of the entire exercise could be in terms of identifying certain deficiencies or limitations in the formerly used concepts, methods, techniques, tools, etc. And attempts to remove them also qualify as contributions to expand the frontier or to push the frontier further. There are problems which still remain problems to be solved or to be taken up in order that the frontiers can be expanded. For example, if we look at the problem of multiple rankings, in the sense that several individuals, they are being ranked by several judges on the basis of a single character. Alternatively, there are several individuals who are to be ranked by a single individual, but on the basis of several characters. And tied ranks are allowed. The result could be a vector of ranks, or you could alternatively have what may be called a matrix, in which the elements could be either +1 or -1 or 0. And the problem is to develop not an average ranking, but a consensus ranking. A big difference between a consensus ranking and an average ranking has to be also recognized. The problem of developing a consensus ranking in the case of multiple ranking problems is a NP-hard problem, still remains to be solved satisfactorily. I was trying to look at how people have tried to solve this problem and how they have themselves pointed out certain limitations in whatever they could come up with. So this is still remaining an open problem, but the attempts that people have been making, they are attempts to push the frontiers forward. There are many other examples of such attempts where people are identifying some limitations, some deficiencies in some existing concepts or methods or techniques, and are trying to remove them to the best of their abilities. A third dimension of the exercise to push the frontiers ahead lies in a more important area where we try to tackle new problems, we throw up new paradigms, we also open up new approaches to solving those problems. Problems like data integration, like metadata analysis, or when we talk of empirical based approach, and even extensions of those, opening up new approaches, as I said, or even talk about data visualization in what is typically nowadays called the big data problem. These are problems which are new. These are areas where attempts are being made to contribute to new methods, not extensions of existing methods, or even to take the help of new approaches. The fourth and the most difficult part of the entire exercise, according to me, lies in the foundational aspects, where you try to look at the basic foundations of probability and statistics and see to what extent they can be helping us in the entire area of scientific research or in the entire area of acquisition of knowledge. In fact, in the last domain, it's quite interesting to look back at some of the criticisms on the foundations of probability or the foundations of statistics and how they have been taken up over the decades to get at satisfactory answers to some of these criticisms. Not all the criticisms have been satisfactorily done away with, and some of them are pretty old but continue to hog us even today. We all know that induction is the very backbone of all statistical inferences. And problems associated with induction have been being pointed out in the history of philosophy since possibly the 18th century in a very concerted manner. But even before the 18th century, deficiencies in induction were being pointed out. I have been reading the Stanford Encyclopedia on Philosophy vigorously over the last few years, and I could identify how there have been solid criticisms with reasons of induction. In fact, David Hume, the great proponent of induction, argues that induction has to be used in science. At the same time, he also points out the important limitation that induction, in terms of going from what has been observed to what has not been, to the past or present, to the future, to the whole from the part, is besought or is, so to say, fraught with the dangers of assuming in an unwarranted fashion that things unobserved, things not yet experienced, will resemble things which have been observed, which have been experienced. This inherent but not explicitly mentioned assumption of resemblance or similarity is very basic to induction. This remains basic but has never been explicitly mentioned. And this is unwarranted in certain situations where one cannot assume necessarily that things not observed are similar to things which have been observed. That things which have been observed so far will continue to remain similar to those which are yet to be observed. And therefore, the question of induction is definitely leading us to some uncertainty that's difficult to resolve. In fact, there are criticisms about induction in the history of philosophy, which even says that induction is the glory of science, but scandal of philosophy. The word scandal is too strong, has not been used at all by David Hume, who is himself a great exponent of induction. But remember the warning given by David Hume, that the assumption of resemblance or similarity, which is inherent in induction, in the use of induction rather, in scientific inference, should not be overlooked. And then comes a strong German philosopher, Karl Popper, who argues that induction is not used in science. What are used in science are conjectures and criticisms. Karl Popper argues that you first develop, maybe on the basis of what you observe, a conjecture. Secondly, you use deduction to calculate the consequences of the conjecture. And thirdly, make use of observation or the observations that you make to refute, to challenge, and if possible to falsify the conjecture. These are the three steps mentioned by Karl Popper. So there have been lots of criticisms about induction. Induction remains the backbone of statistical inference. And the other problem is about going from inferencing to decision making. We make use of statistical decisions these days, and decision being the problem of choosing one among several alternatives opens up a Pandora's box, in the sense that you are now facing a whole host of approaches, a whole host of criteria, a whole host of methods to choose that single alternative. The problem is to choose one of many possible alternatives. And the solution is a multiplicity of approaches, a multiplicity of methods, a multiplicity of procedures. Then are you back to the same problem? Therefore, can I say that no decision problem is solved? It continues to remain a decision problem. I would end up my brief remarks while leaving the floor to Professor Tathagata Bandyopadhyay about the black swan events mentioned by Nicholas Taleb. The black swan events are events which are very rare, and that way we associate a very low probability of occurrence with them. The resulting feature is that you can associate only sparse data available on any black swan event. The second characteristic of a black swan event is that their potential consequences are huge. They've got very severe consequences. They have low probability of occurrence, but they've got potentially very high consequences, very severe consequences. And the third disturbing characteristic feature is that in hindsight, not foresight, in hindsight, people insist that they were obvious. So these are rare events on which you get sparse data. They have potentially severe consequences, and people insist that they were obvious in hindsight. And how risky is the application of probability or of statistical methods which are data-based in making a response to what are called black swan events or surprise events. These are issues which continue to hog those who try to delve into the depths of probability and statistics. But I'm sure that with the contributions of active young researchers, not an old guy like me, well, some of these fundamental issues will get resolved, and statistics and probability will get a prime seat in the quest for new knowledge. With these few words, I have great pleasure in formally inaugurating, which could have been avoided, of course, this International Symposium on Probability and Statistics. Thank you.
Thanks a lot, Professor Mukherjee, for sharing your valuable thoughts. Before starting off with the keynote address, I will request Dr. Arindam Gupta, Joint Convener of ISPS 2022, to deliver the vote of thanks.
Good afternoon, everybody. As we come to close of inaugural session, it is my privilege to propose a vote of thanks. At first, I want to share my heartfelt gratitude to inaugurator Professor S.P. Mukherjee sir, for former Centenary Professor of Statistics, University of Calcutta, and keynote speaker Professor Tathagata Banerjee sir, Dhirubhai Ambani Institute of Information and Communication Technology, Gandhinagar. Despite their busy schedule, they deliver their valuable lectures. Sir, on behalf of organizing committee, we are assuring you that we will do our level best to fulfill your desire regarding our association. Again, on behalf of organizing committee, we express our earnest thankfulness to invited speakers, contributory speakers, and participants. I also want to share my big thanks to the chairman, convener, and other organizing committee members. Without their kind cooperation, we could not able to organize this seminar. I must mention our deep sense of appreciation for our technical support team. Without their sincere response, the event would have remained impossible. Again, a big thank you wishes to share to all the participants for their positive response. Thank you all.
Thanks, Dr. Gupta. I'll now request Professor S.P. Mukherjee to chair the keynote address and conduct the session.
Well, we have a very distinguished speaker for the keynote address, my former student, a very affectionate one, Professor Tathagata Bandyopadhyay, who was also a very renowned faculty member in the University of Calcutta Department of Statistics. He also taught in the Indian Institute of Management, Ahmedabad, before moving to the Dhirubhai Ambani Institute. He is grounded on reality and can enlighten us on conceptual aspects as well. We all look forward to his presentation. Professor Tathagata Bandyopadhyay.
Thank you very much, sir, for the introduction. And I'm still a student of you. And to the organizers for inviting me. And actually, they asked me to shoulder some responsibility, which is, I find, very heavy. So initially, I didn't agree, but somehow Monisha was saying, no, please do this. So I agreed on the request of Monisha. So now what I will have to, I have to share my screen.
Tathagata, we can also see your face.
Hi, yes, you will, but let me share my screen.
Thank you.
Okay. No. So can you see my screen now?
Yes, sir, it's visible.
Okay.
Yes.
Okay. So the title of my talk is Some Random Thoughts on Statistics as a Discipline. So because I read a lot on many things which are happening around us, and I thought that maybe I will share some of my thoughts, of course not all, it's too many, so which I think may be good to share with all the statisticians and probabilists, whoever is there. This is a good platform to share my thoughts, and it's up to you to accept or not to accept. So let me, as Professor Mukherjee was telling, that I taught in 3 institutes. I began my career in Calcutta University Department of Statistics, and I taught there from 1984 to 2005, 21 years I spent there. After that, I moved to IIM Ahmedabad. There I spent more than 17 years as a faculty. And after my retirement in 2021 October, I took up this new assignment. And in this lecture, I will wear 3 hats. The first hat would be as a management teacher, okay? So in IIMA, I learned a lot, okay? Which I would not have been knowing if I decided to continue in Calcutta University. So management teaching is different from teaching in a university setup. So my first part of the talk would be as a management teacher. And in second part, I will wear the hat of a statistician, possibly which I learned in Calcutta University as a teacher as well as a researcher. And in the third part, now I have joined a university, an institute, which is basically a technology institute. And now I talk to people who are basically doing machine learning and AI kind of research. And I am learning a lot from them also. So these are the 3 parts of my talk that I will touch upon. And there is one more thing that I need to tell you, that I believe in Professor Feynman's statement that if you cannot explain your thoughts to a class 6th grade student, then possibly you don't know enough. But in my case, possibly I don't know enough, but still I will try to explain it in a language which can be even understood by a grade 6 student, okay? So the first part of my talk is a logical framework to draw conclusions from data, okay? So this I used to say in my class in Management Institute, because in Management Institute, what I used to teach them, I used to give them a data, and then I say, okay, see, using your common sense and kind of analytical bent of mind, you can ask a lot of questions from this data. So I think this is a very interesting aspect of statistics, that even in our life, we can use statistics because what I learned from statistics, a logical framework to draw conclusions from data. And if we can draw a conclusion from data, we feel more comfortable. Instead, if we say our opinions could be many, but when you are talking from data, you feel much more comfortable. So that is the first part. And second part is how the discipline has shaped up, starting from 1920s or before that, till the point of today, till today. So I'll pick up only one topic, which I think is very important now for the statisticians, and they have done pioneering research in that area, that is causal inference. I will talk a little bit about causal inference. And the third is I will talk about 2 crises that statisticians have faced in the last decade and how to overcome that crisis. It's up to you. You need to decide. I will talk about that. So I will tell you 2 stories which are around 300 years apart. Okay. So one is about bills of mortality and population size of London. Many of you possibly know that John Grant was considered to be the first statistician in the world because of his analysis of data of bills of mortality that he obtained from bills of mortality. And he used a particular kind of logic that I actually liked a lot. And I think that is what we do in a sense. And second is Fermi logic, which is also well known. I stumbled upon it, very fortunate to stumble upon it. And Enrico Fermi, possibly you know, the Nobel laureate physicist, he won Nobel Prize for his contribution in nuclear physics. And he won it at the age of 37, and he went to Stockholm to receive his prize in 1938. from Stockholm, he straight moved to USA with his family, because in Italy, he was an Italian. In Italy, he was facing some problem because of his origin. He was a Jew. And so he moved to USA, and he immediately joined Columbia University, then University of Chicago. And he was credited to build the first nuclear reactor in University of Chicago. And he was very much involved with Manhattan Project, which developed the first atom bomb. But he also died very young at the age of 51. So this Fermi logic I will talk about. So let me talk about bills of mortality a little bit. So what is bills of mortality? Actually, it's a weekly gadget that reports the number of christening and the burials in different parishes of London. It started in the beginning of 1600 because of lots of plague happened in London in 1600 and that time. So to forewarn the people that something is coming, some epidemic is impending, so they want to record the number of christening and number of burials in every week. If something unusual, unusual pattern is discovered, then possibly they will look for the pattern. So I will go to Grant's logic. So actually Grant wrote a book. I am not getting into that. I am just discussing one of his problems, that is how he estimated the population of London in 1661. So his logic is very simple. Suppose the annual number of births is B. Then first assumption, every woman in the childbearing age group gives birth to one child in every 2 years. That means in today's language, general fertility rate is half. Thus the number of childbearing women would be naturally 2B, okay? And then go to assumption 2, number of women in the age group 16 to 76, that means full age group, is twice the number of women in this childbearing age group and is same as the number of households. That means he was assuming that in each household there is only one woman in that age group, and thus the number of households is 4B. Assumption 3, average household size is 8. Man, wife, 3 children, 3 servants or lodger. This gave him the population size is 32B. Now the question is how to calculate B. He didn't depend on the number of christening that happened in 1661 as an estimate of B, because he knew that after the plague, the christening or baptism was not that popular. So what he did, he computed the ratio of number of christenings to the number of burials over the non-plague years before 1642. And he found is 12/13. But on the other hand, number of burials in 1661 should not be wrong. It would be accurate. So 13,000 was the number of burials. So 13,000 into 12/13, it gave him 384,000. And to account for the population in several other parishes outside the city, he actually found the number of burials was about 1/5 of the city proper. So he inflated 384,000 by 20%, and he got 460,000 as the population of Greater London. So you see, this exactly similar kind of logic I saw Fermi used to pose similar kind of problems to his students in physics class. That is very important. Fermi used to say these are non-standard problems. Getting precise estimates of these numbers are either impossible or need huge efforts in terms of time and money. Fermi is known for his ability to make fast and excellent approximate calculations with little or no concrete data. The method doesn't guarantee correct results, but it does give a first approximation which may be off not more than a factor of 2 or 3. So let me go to the problem directly. So this is the famous problem I will discuss. How many piano tuners are there in Chicago? He used to pose this problem to his first year physics students in University of Chicago. And someone wrote that the students used to give him a blank stare because they have no idea how to find an estimate of that. And then he will proceed like this. from the almanac, we know 3 million people live in Chicago. Now assume that an average family has 4 members, so that the number of families in Chicago must be 750,000. If 1 in 5 families owns a piano, there will be 150,000 pianos in Chicago. If an average piano tuner services 4 pianos a day and work for 5 days a week, that means in a week, he or she will service 20 pianos. And then he assumed this piano tuner had a 2-week vacation in the summer, so he or she will work for 50 weeks. So 15 to 20 is 1,000 pianos. So the number of piano tuners must be 150,000 divided by 1,000, which is 150. So you see, the two logics, I think, very similar. You are making some assumptions, as Professor Mukherjee was saying, that you see that in both these assumptions, on the average, it is kind of weak law of large number we are using. Some kind of stability, frequential regularity is assumed inside this logic. So I think that statistics gives us a framework to think from data and to draw conclusion from data. That is my definition of statistics, because I found it very useful when I was teaching the management students. Okay, so this is the first part of my talk, and now I am coming up to the second part. So we all know that the present state of statistics was developed by Galton, followed by Pearson, Fisher, Jeffries, Mahalanobis, Neyman, and later by Rao, Cox, Ifron, and Rubin, among many others. And I am not getting into all of this because it's impossible. I have picked up one particular topic, which is causal inference. The reasons are many. One is it's an emerging area of research for many fields, not only statistics. You go to economics journal, you go to computer science journals, you will find people are talking about causal inference. And possibly you know that Joshua Angrist and Guido Ibanez and Professor Hart, they got Nobel Prize in 2021 for developing methodologies as well as contributing to the applications of causal inference in the field of economics. And before that, of course, in 2019, Abhijit Banerjee, Esther Duflo, and there's another professor from Harvard, they got Nobel Prize for bringing randomized controlled trial into the field of economics. So there are 2 Nobel Prizes that went to this area in the recent past. And thirdly, I will say that I was interested because I had a little interest in this. And recently I actually read a thesis which is written by Ambarish Chatterjee, Gaurango's son. It was a very, very interesting thesis. He did his PhD from Harvard, and I requested him to send his thesis, and he considered some very interesting problems. I will tell you about one interesting problem that that question was asked to me by a student in management. So what was this? So we talk about random sampling, okay? I am explaining random sampling to the students. And I said random sampling is kind of giving in unbiased. There is no selection bias. So one question one day asked me, sir, you are saying it is unbiased. Suppose I am tossing a coin and the coin is unbiased. And I tossed it 10 times, all 10 times I get hit. So my estimate will be very bad. And I know in some cases that this is a very bad sample. So what did you do with that? I didn't have any answer to that. So I had this question in mind. Then I came up with 2 papers written by Rubin and his student, and one appeared in Annals and the other appeared in JASA. Rubin talked about this problem. He said it is re-randomization. So he was saying that Fisher knew about this, but Fisher was silent. It was intentional silence, because if you asked Fisher verbally, he would have said you would have to re-randomize. So, but what is the problem of re-randomization? once you re-randomize, that means you know these are bad samples, I will have to get rid of these. So you are actually considering a truncated distribution. The tail you are cutting off. So when you have a truncated distribution, then if you think about the T statistics, F statistics, all these sampling distributions will go haywire. So in these two papers, they actually found in such situations what would be the asymptotic distributions of these simple statistics. One appeared in JASA, the other appeared in Annals. Those are very interesting paper. And Ambarish also attacked the same problem, but he approached it in a different way. I'm not getting into that. Okay, so to talk about causal inference, the first important thing is Rubin's potential outcome framework, because Rubin more or less single-handedly developed this. What was the idea? The idea is very simple. Suppose I got a headache. So I have two options, either take an aspirin or I will not take an aspirin. So if I take an aspirin, there would be some scale, maybe 1 to scale. What would be the status of my headache after 1 hour? So that is Y1. If I don't take aspirin, what would be my status of headache after 1 hour? Y0. So what is the causal effect for me? It is Y1 minus Y0. But we know, since it is impossible to observe both Y1 and Y0, it is impossible to estimate tau, to find tau. And this was called the fundamental problem of causal inference in a paper by Holland in 1986 JASA. It was a discussion paper. So another interesting example of causal inference that economists have been studying for a long time is whether going to college increases future earning. So again, the same problem. If you go to college, I can't go back in time, and I can't tell you, you don't go to college. So I will have only one part of the data. And Rubin, in one of his lectures, was saying that as a physicist, because he had his physics degree from Princeton, undergraduate physics degree, he was saying, as a physicist, I know it for a long time. I'm used to this kind of thing. He talked about Heisenberg's uncertainty principle. At any point of time, you cannot measure the position and the momentum of a particle at the same time precisely. If you want to precisely measure the momentum, your measure of position would go haywire. If you want to measure position, you will not get a good estimate of momentum. So he said that this is because of his physics background, he could also think this problem is also a missing data problem, because you have one data is missing. So Rubin did a lot of fundamental work, both in missing data and potential causal inference. And because of his possibly physics background, he could think about all this easily. Okay. So then the question is, what is the problem? Problem is this, that I cannot solve this problem. Okay. But there is a statistical formulation of problem possibly that can be solved. Think about a population of n units and consider the tau, average tau for all the population units. But then what should you do? What do you do? We create two groups. One group is given treatment, the other group is given placebo or control. And then you find a mean and take the difference that will kind of estimate of tau. But Rubin said, no, that cannot be, because there could be selection bias. Who are getting 1 and who are getting 0, they are intrinsically different. So by doing this, you can get an estimate of tau only if your assignment is random. So that means randomization is very important to get an unbiased estimate of tau. So randomization plays a very, very big role in causal inference. Then Rubin talked about another principle, where actually randomization is not enough. For example, first, the outcome of one unit will not interfere with the outcome of other units. This is often called spillover effect. That means both me and you are thinking about whether taking aspirin or not. Suppose I have taken aspirin, but you have not taken aspirin. We are in the same room, and you are complaining so much about headache, it will create a headache in mine. So that means that this is some spillover effect. So outcome of one unit will not interfere with the outcome of other units. And there are no different forms or versions of each treatment level. That means the dosage of aspirin should be same for everyone. So these are called SUDVA, stable unit treatment value assumption. But causal inference in social science, that was randomized control trial was brought in by this Michael Kramer. Actually, I was talking about this guy from Harvard, Abhijit Banerjee and Esther Duplo. And they won Nobel Prize for bringing randomized control trial in solving important problems in economics. But you see, randomized social experiments are expensive to field and may be slow to bear fruit, okay? And while research funds are scarce and life is short, this is by Joshua D. Angrist, who got Nobel Prize in 2021, David Card, Joshua Angrist, and Guido Imbens. They won Nobel Prize in 2021 because of their contributions to both methodology and applications of causal inference using observational studies. That is, you don't randomize, but you are using observational studies. Specifically, the use of natural experiments to answer important economic questions. What are natural experiments? I can give you a very simple example. Before COVID, everyone used to have offline classes. During COVID, everyone got online classes. What is the causal effect of offline and online, the difference? This is a natural experiment happened because of some situation. So they talked about several such natural experiments, and then they applied econometric techniques to solve those problems. And because of that, and David Card considered this kind of problem in labor market. He considered, okay, if the minimum wage is increased, how it affects the unemployment. It's a very difficult question to answer theoretically. So these are the kind of problems they considered, and because of that, they got the Nobel Prize in 2021. But here I need to tell you an interesting fact. Fisher was the first to propose actually doing randomization. You see, doing randomization, doing is very important. In the last chapter of first edition of Statistical Methods for Research Workers. Before him, there were other people who talked about it in like, had you randomly assigned, then the expectation would be like this, variance would be like this. Neyman talked about it in his 1923 master's thesis in Poland on agricultural experiments. However, Fisher was the first to propose that you should actually randomize. So doing randomization and thinking about randomization hypothetically, these are two very important differences. So here is an expert, Constance Reed's book. It's a biography of Neyman from life. Here is an interesting quote. Neyman is saying, because he was saying, you should be credited for talking about randomization before Fisher. But Neyman said, I treated theoretically and unrestrictedly randomized agricultural experiment, and the randomization was considered a prerequisite to probabilistic treatment of the results. This is not the same as the recognition that without randomization, an experiment has little value irrespective of the subsequent treatment. The latter point is due to Fisher, and I consider it as one of the most valuable of Fisher's achievements. Think about the humility of the guy. At that time, Neyman and Fisher, they didn't look at each other's face because of the problem of Neyman-Pearson testing theory and Fisher's significance theory. They hated each other. But even after that, Neyman said that the credit should go to Fisher, should not go to him. Fisher's another achievement, besides so many others, to propose randomization test, a very intuitive test, without any distributional assumption. If I had time, I would have gone into that using simple examples, which is 6 students would understand, but I don't have time. And also, use of randomized experiment in the domain of quality by Deming after the Second World War in Japan, also afterwards by Taguchi, led to huge improvement in the quality of Japanese products, and thus led to economic recovery of Japan. Possibly Professor S.P. Mukherjee can talk on this for hours, what Deming did in the quality field. But that is, I don't know so much. Professor Mukherjee is an expert in this field. And an interesting sidelight, use of randomized experiment was limited to units with no consciousness. think about this. I am not saying inanimate objects. I am saying no consciousness. Because someone may say agricultural experiments, trees are not inanimate, they are animate. So why are you saying that? I am saying no consciousness. The Medical Research Council trial for streptomycin for pulmonary tuberculosis in 1948 was considered as the first randomized clinical trial, ushering in the era of randomized experiment with conscious units. Although after that, it took a long time to transport RCT to conscious units, but nowadays you can see so many clinical trials are happening and they are conducted by the pharmaceutical companies. But it took a long time to transport RCT for conscious units. Now I will talk about crisis, as I told you. So the first crisis that statistician faced is p-value crisis. Possibly many of you know. Recently, we faced a huge flack from the scientific community on the misuse of p-value as measured of strength of evidence in null hypothesis testing framework. John Ioannidis, he's a very, very interesting guy. He is a professor of Stanford in evidential medicine. I follow him because he writes something always very interesting. In his 2005 PLOS medicine paper, it is highly cited, I think more than 30,000 cited. Why most published research findings are false. Identified the misuse of p-value as the key factor for the creation of the current chaos in science. And he went on saying this, several methodologists have pointed out that the high rate of non-replication, lack of confirmation of research discoveries is a consequence of the convenient yet ill-founded strategy of claiming conclusive research findings solely on the basis of a single study assessed by formal statistical significance, typically for a p-value less than 0.05. Research is not most appropriately represented and summarized by p-values, but unfortunately, there is a widespread notion that medical research articles should be interpreted based only on p-values. So he lamented in this article. In 2015, in another highly cited article published in Science, entitled Estimating the Reproducibility of Psychological Science, the authors, here is a nuanced difference in meaning, replicability and reproducibility. I also learned it from Professor S.P. Mukherjee. Replicability means you are replicating an experiment independently, but reproducibility means, suppose someone did an experiment, you are actually using the same setup in terms of everything, and you are trying to reproducing his results. So this paper was about reproducibility. The authors, through open science collaboration, worked with the authors of the papers published in top 5 psychological journals to reproduce their results. And they found 50% of the less than 50% of the significance results would be reproduced. And so it's a problem. So again, it is based on p-value. So they said it is based on p-value. So what are the issues here as a statistician? P-value is a statistic. Naturally, it is subject to sampling variation. In view of this, the dichotomous rule that we are so familiar with, reject the null hypothesis if p-value is less than 0.05, don't reject otherwise does not make any sense. It should be considered in continuum. Besides, there are many other important factors like the effect size, the specifics of data collection, curation, and even the intention and motivations of researchers are critical for inference. So you need to report everything. So only p-value cannot tell you whether the result is significant or not. And secondly, there has been great concern over two common misinterpretation of p-value as the posterior probability of rejection of non-hypothesis when it is true. But it is completely wrong. We know that if I give you a very simple example and tell you that can you find an analytical expression for this? Impossible. You need to do some computer simulation to understand this. And Barger actually did that through he developed a software called Applet, which is available in his website in due. You can see that what is the consequence of misuse of p-values. And unfortunately, most of the textbooks, this is the most important thing. Unfortunately, most of the textbooks in statistics fail to communicate that the Neyman-Pearson testing framework is completely different from significant testing framework. Fisher proposed p-value as a measure of strength of evidence against the null hypothesis. He never proposed reject, do not reject kind of framework based on p-value, which Neyman-Pearson theory proposes. Unfortunately, most of the textbooks, after proposing Neyman-Pearson framework of testing of null hypothesis, take an easy route to carry out the test by computing p-value. And that's why it created a huge problem in the scientific community. Musso described in Nature News, very funnily, when Fisher and Neyman were busy fighting with each other about their approaches, without an understanding of either approach, the non-statisticians began to write statistics manuals for working scientists and created a hybrid system that crammed Fisher's easy-to-calculate p-value into Neyman-Pearson's reassuringly rigorous real rule-based system. Berger wrote in Stat Science, the disagreement between Fisher and Neyman has had a significantly deleterious effect upon the practice of statistics in science, essentially because it has led to widespread confusion and inappropriate use of testing methodology in the scientific community. So this is about this, but what American Statistical Association did, they are finding that a situation is created where they have to come up with some explanation. Sensing the gravity of the situation, they came up with a statement, ASS statement on p-value. Everyone knows it was written in 2016. So Don Berry summarizes the reaction of ASS very nicely. He's saying our collective credibility in the science community is at risk. We cannot excuse ourselves by blaming non-statisticians for their failure to understand or heed what we tell them. We must communicate better, even if we have to scream from the rooftops, which is exactly ASA is doing. Interestingly, still around 1 million papers get published each year that uses null hypothesis testing framework. And I think the misuse of p-value still continues. Actually, I looked at 1 million papers. Actually, in every year, more than 7 million papers get published. So I got to know about it from a lecture of Donovo. So he was saying 1 million papers per year. I said, it's impossible. Then I found, yes, it could be. More than 7 million papers get published in every year. So 1 million paper could be using this null hypothesis testing. Now I will talk about the new technology. It is, I don't know whether it's a crisis, but it's something you need to take notice about. So you see that it was told by Bryman in his 2001 statistical science paper, very nicely. Statistics starts with data. Think of the data as being generated by a black box in which vector of input variables x, which are independent, go in one side, and on the other side, the response variable y come out. Inside the black box, nature functions to associate the predictor variables with the response variable. But there are two goals in analyzing data. One is prediction, to be able to predict what the responses are going to be to future input variables. The other is inference. Implicit in this particular culture is this, that there is a true model in the black box. And we need to discover that true model. Once we discover the true model, we fit the model to the data, and then we draw a lot of inferences from that. And it is interesting, Bryman says that thinks that 98% of all academic statisticians belong to the inference culture. And 2%, including him, belongs to the prediction culture. Because Bryman has a checkered career. He was initially in the academics, then he spent some time in corporate, kind of consulting, statistics consulting. And then again, he came back to Berkeley as a professor. So because of that, possibly Bryman, at that point of time, thought that prediction is very important and we are possibly neglecting it, okay? So the new technology, AI/ML, it's nothing but the technology driving prediction culture. AI/ML are now ubiquitous in almost all spheres of life: speech recognition, machine translation, image recognition, medical diagnosis, autonomous cars, precision farming, smart city, Internet of Things, to name a few. There are so many things. Andrew Weil, he is a very famous professor of Stanford in computer science. I was hearing a lecture and he was saying, I think we live in a world where just as electricity transformed almost everything almost 100 years ago, today I actually have a hard time thinking of an industry, major industry, that I don't think AI will transform in next several years. So this is what AI/ML, they are now ubiquitous. And if you know AI/ML, it's easy to get jobs, I can tell you, because now I talk with my younger colleagues, they are all doing research in AI/ML. And I am learning a little bit of that. So what AI is doing, artificial intelligence is doing, it turns out that almost all these ridiculously huge amounts of economic value of AI is driven by only one type of AI, which is supervised learning. What is supervised learning? What actually Bryman said, given a sufficiently large amount of data on XY, that means input and output, the algorithm automatically figures out a mapping from X to Y. You don't have to think about any mapping. You don't have to give any model. The algorithm itself will learn from the data and figure out a mapping. The automated system then can be used for predicting Y for a new X. This is exactly what AI/ML is doing right now. So you see, for example, if my email is my input, the output would be spam or not. Image is an input, object in this image. Is it cat, is it dog, or is it a bird? Audio clip I give, it will give me text. English text, French translation. I give text and then it will give me the corresponding audio. There are so many other applications. These are the basic few. So it is actually all around us. Our life is getting changed by the applications of AI and ML. So, but it is an interesting question that I had in mind, but I found it in the lecture of Andrew Weil. Andrew Weil said that AI has been around for many years, in fact, several decades. But maybe in the last 10 years or so, AI has really taken off. So why is this? Why AI is only now taking off? So here is an explanation. So suppose I draw a graph. And here is the amount of data. Amount of data means I'm talking about XY. Okay. And then here is the performance of ML algorithm. Okay. And that is measured in terms of predictive accuracy. Say. So earlier he was saying the curve was like this. That it is like this, and then it gets flattened. That means traditional ML algorithm, which is basically support vector machines, artificial neural network, simple artificial neural network. If you give data, after a certain point of time, it doesn't know how to do with this additional data. It cannot get on improving its performance. But what happened now, because of technological development, particularly GPU, graphical processing unit, and high performance computing, as well as what you possibly everyone heard that they called deep learning net. So this is basically a multi-layered artificial neural network. This is now happening something like this. That means if you use a slightly bigger neural net, if you use a much bigger neural net, big neural net, then the curve would be like this. That means as you are making the neural net bigger, your performance is improving. But on the other hand, if you have to use bigger neural net, you need to have a huge computing power, and that is possible. That has been made possible by the recent technological development in different parallel processing, high performance computing, and other kinds of GPU, all these things. So this is why now If you have a huge amount of data, your prediction accuracy would be very, very high. And it was proved in many instances. Okay, so now the question is, in the backdrop of all this development, especially with the digitization of data, the challenge that the statisticians are facing now is how to stay relevant. Possibly we need to pause, reflect, and introspect. Should we create a new breed of statisticians who would be able to process, manage, and extract information from huge data, or should we continue to do what we are doing in classroom now? So possibly we need to think about it. Possibly we missed the bus already, and if we still continue to do this, I don't know what will happen. Okay, and let me now quote Hedley Wickham, who got Pops Award, which is the Nobel Prize of Economics kind of thing, in 2019. And when he got Pops Award, I was surprised. Wickham got Pops Award. What is his contribution? He developed what is known as RStudio. So because of developing RStudio, he got the Pops Award. Now I understand, yes, he should be given Pops Award. So it is his quote: the best way to impact the world as a data scientist or statistician is to be useful. It doesn't matter how great your work is if no one knows about it. If you want to have an impact on the world, you need to think about marketing. While many academics think marketing is a dirty word, it is not actually about tricking people into using your tools. Instead, it's about making people's lives easier by letting them know about your awesome tools. And exactly that is the AI/ML community is doing. I can go on AI/ML community, how they are doing, but I don't have time. So thank you for your patience here.
Thank you very much, Tathagata, for your very, very interesting, useful, and impressive presentation. You have covered a wide variety of topics, and you have made at the end a passionate appeal that statisticians should think over certain issues to stay relevant. And even in that context, proper words have to be understood in a proper manner. The word marketing has to be also understood in a proper manner. We have to make other people's lives easier by letting them know about some tools that we are developing to help them extract more information, to help them in making decisions, to help them in making their lives easier, more comfortable. Thank you once again. It's very, very instructive, informative, and interesting. If the organizers permit a few minutes time, we can have a few questions, but otherwise a keynote address is not normally open to questions.
Yes, sir, we can have a few questions from the audience.
Okay. Only a few questions can be raised by the audience, and the speaker will be happy to respond to them. But you can accommodate only a very few.
I guess we have a question from Dr. Shoris Dash.
Thank you. So my question is, there are one of the problems recently that AI ML have faced the crisis that some of the big models can't, particularly in the face recognition, cannot identify the the face by female or faces of the African American communities, and it is being called machine bias. And it is not like only we are facing the crisis. I think AI is also facing this kind of bias crisis. Any comment on that?
Yes, actually, I had several slides on trustworthy AI/ML, but I removed it because I know that in 40 minutes I cannot cover that. Trustworthy AI/ML is the emerging area of research in AI/ML, and in trustworthy AI/ML means the system, the ML algorithm that we are using should be unbiased, should be fair, and should be explainable. That is another problem. Should be robust, and should have causal inference can be done from that. But the problem I find actually I am reading a lot about trustworthy AI/ML because of my colleagues in the institute. The problem is facing what is fair. The definition of fair is very, very difficult because to different stakeholders, the definition of fair is different. And here, the idea from philosophy, the idea from psychology, the idea from laws, all are coming in. And I'm happy that Shourish pointed out that so that I can talk a little bit about that. That's a very, very interesting area. And I have been reading papers on that. And I have created a group of people in my institute. We met twice a week to discuss about papers in trustworthy AI/ML. That's a very important area, as you pointed out, Shourish.
A question from Dr. Parthonil Roy.
Yeah. Hi, Tathagata, thank you very much for a very nice talk. I really enjoyed it. So I saw that you're saying something to the statisticians. Any advice for the probabilists?
Probabilists are safe, I think. They are doing their work, and those are applicable in various other fields. Okay, they don't have to. But statistics, I think they have a responsibility. Okay, so they are actually feeding methodologies to the practitioners who will be using it. But probability may not be directly used by the practitioners. Probability will be used by people in statistics. Probability will be used by people in physics. Probability will be used in computer science. So I think it's a core discipline. I think there is no problem. I think you are safe, Pratham.
Okay, thank you.
Maybe one last question, Dr. Himadri Ghosh.
Sir, you told that prediction accuracy will be very high, okay? Am I audible?
Yes, yes, yes.
Yeah. So in case of time series data, we use the prediction error variance. So there must be some error. And if you nullify the error, if I have 10 data points of time series, we can fit a polynomial of degree 9. The fit is very good. So what kind of prediction you are mentioning here?
No, Himadri, you see that all AI/ML algorithms, they solve the classification problem.
It is a classification problem.
The classic. All you see that almost all applications of AI/ML are basically classification problem.
No regression problem is here.
Regression was traditional AI/ML, but in the deep learning network, the input is feature vectors, and output is basically you have to classify whether it's a cat, whether it's a dog, something like that. Whether this particular sentence is actually this. So basically it solves a classification problem. That's why I think it is easy to measure the prediction error.
Okay. The prediction in that sense. Okay.
In that sense, yes.
Thank you.
I
Thanks a
believe
lot.
there are no other questions. We should once again thank Professor Tathagata Bandyopadhyay for his very interesting, informative, and almost, what I could say, a wonderful talk.
Last, I would like to talk. I had several slides on that. I also removed because I heard many times statisticians says that big data is a hoax. It is not a hoax. If anyone is interested to see how big data can be used in the research of economics, please visit Raj Chetri's website. He is a fantastic researcher, and how he is using big data to solve problems in causal inference. So it's not a hoax. Please don't ignore it. I'm saying.
Thank you. Thank you for the information. Diwan, what do we do now?
Thanks a lot, Professor Mukherjee, for chairing the session. Your presence and your views are always an inspiration to all of us. Sincere thanks to Professor Bandyopadhyay for the very interesting session. We could not have asked for a more befitting start to the International Symposium on Probability and Statistics. We'll now start with our first technical session on applied probability.
Welcome to the first technical session on applied probability.